Welcome to this new session dedicated to exercises on function, composition, and solving equations. In this video, we will carefully go through several typical exercises ranging from rational functions to biquadratic and irrational equations, including compositions involving square roots. Exercise 1. Composition of rational functions and domain of definition. Let the functions u and v be defined as follows. U of x is equal to the quotient of x plus 1 by x minus 2. V of x is equal to the quotient of 1 by x plus 3. The task is to determine the domains of definition of u and v. Express the composite function f equal to v composed with u in terms of x. Determine the domain of definition of the function f. Exercise 2. Composition and solving of biquadratic equations. Let the function h be defined by h of x equal to 2x to the power of 4 minus 9x squared plus 4. Identify h as a composite function of two functions f and u, such that h is equal to f composed with u, where u of x is equal to x squared. Solve the equation h of x equal to 0 using a change of variable. Exercise 3. Composition involving a square root and a rational function. Let the functions f and g be defined as follows. F of x is equal to the square root of x plus 2. G of x is equal to the quotient of 1 by x minus 1. The task is to determine the domain of definition of f and the domain of definition of g. Determine the expression of h equal to g composed with f of x. Determine the domain of definition of h. Exercise 4. Implicit composition and irrational equation using substitution. Let the equation E be x minus 5 times the square root of x minus 14 equal to 0 over the set of non-negative real numbers. Define a substitution capital X equal to u of x in order to transform equation E into a polynomial equation in capital X. Solve the polynomial equation in capital X. Determine the solution set S of equation E. Solution of exercise 1. Domains of definition. The function ux is defined if the denominator x minus 2 is not equal to 0. That is, if x is not equal to 2. Therefore, du is the set of real numbers excluding 2. The function vx is defined if the denominator x plus 3 is not equal to 0. That is, if x is not equal to negative 3. Therefore, dv is the set of real numbers excluding negative 3. Expression of the composite function f equals v composed with u of x. We have f of x equal to v of u of x. Therefore, f of x is equal to v of the quotient of x plus 1 by x minus 2. This means that we replace x by u of x in the expression of v of x. F of x is equal to the quotient of 1 by the quotient of x plus 1 by x minus 2 plus 3. To simplify, we write the denominator as a single fraction. F of x is equal to the quotient of 1 by the quotient of x plus 1 by x minus 2 plus the quotient of 3 multiplied by x minus 2 over x minus 2. This gives f of x is equal to the quotient of 1 by the quotient of x plus 1 plus 3x minus 6 over x minus 2. We then obtain f of x is equal to the quotient of 1 by the quotient of 4x minus 5 over x minus 2. Inverting the fraction in the denominator gives f of x is equal to the quotient of x minus 2 by 4x minus 5. Domain of definition of f. The domain of f is the set of real numbers x such that, first condition, x belongs to the domain of u, therefore x is different from 2. Second condition, u of x belongs to the domain of v, therefore u of x is different from minus 3. Let us check the second condition. U of x equal to minus 3 means that the quotient of x plus 1 by x minus 2 is equal to minus 3. Since x is different from 2, we can multiply both sides by x minus 2. X plus 1 is equal to minus 3 times x minus 2. This gives x plus 1 equal to minus 3x plus 6. Rearranging the terms, we obtain 4x equal to 5. Therefore, x is equal to 5/4. Thus, the function f is not defined when x is equal to 2 or when x is equal to 5/4. Conclusion: the domain of definition of f is the set of real numbers excluding 2 and 5/4. Before diving into what's next, don't forget to subscribe to stay updated with all the new content. If this helped you, give it a like, share it with someone who might need it, and leave a comment. Your questions and feedback help everyone grow. Solution of Exercise 2. Identification of the composite function. We define the function u such that u of x is equal to the square of x equal to capital X. Then, the function h of x is equal to 2 multiplied by the square of u of x minus 9 multiplied by u of x plus 4. The outer function f is a quadratic polynomial defined by f of capital X equal to 2 multiplied by the square of capital X minus 9 multiplied by capital X plus 4. Thus, h of x is equal to f of u of x. Solving the equation h of capital X equal to 0. The equation 2 multiplied by the 4th power of x minus 9 multiplied by the square of x plus 4 equal to 0 becomes 2 multiplied by the square of capital X minus 9 multiplied by capital X plus 4 equal to 0 by setting capital X equal to the square of x. We compute the discriminant delta in order to solve the equation in capital X. Delta is equal to the square of 9 minus 4 multiplied by 2 multiplied by 4. That is 81 minus 32 equal to 49. Since delta is greater than 0, there are two solutions, capital X1 and capital X2. The first solution, capital X1, is equal to 9 minus the square root of 49, the whole divided by 2 multiplied by 2, which is 9 minus 7 over 4, giving 2 over 4, that is 1/2. The second solution, capital X2, is equal to 9 plus the square root of 49, the whole divided by 2 multiplied by 2, which is 9 plus 7 over 4, giving 16 over 4, that is 4. We now go back to the initial variable x by using x squared equal to capital X. First case, if the square of x is equal to 1/2, then x is equal to the square root of 1/2, that is square root of 2 over 2, or else x is equal to minus the square root of 1/2, that is minus square root of 2 over 2. Second case, If the square of x is equal to 4, then x is equal to the square root of 4. That is 2. Or else x is equal to minus the square root of 4. That is minus 2. The set of solutions of the equation h of x equal to 0 is therefore the set formed by minus 2 minus square root of 2 over 2, square root of 2 over 2, and 2. Solution of exercise 3, domains of definition. The domain of f is the set of all real numbers x such that x plus 2 is greater than or equal to 0. That is, all real numbers greater than or equal to negative 2. The domain of G is the set of all real numbers except the number 1. That is, all real numbers other than 1. Composition. The function h is equal to g composed with f of x, which means h of x is equal to g of f of x. So, h of x is equal to g of the square root of x plus 2. Therefore, h of x is equal to 1 divided by the square root of x plus 2 minus 1. Domain of definition of h. The domain of h is the set of all numbers x belonging to the domain of f, such that f of x belongs to the domain of g. In other words, the domain of h is the set of all numbers x greater than or equal to negative 2, such that the square root of x plus 2 is not equal to 1. The condition, the square root of x plus 2 is not equal to 1, is equivalent to saying that x plus 2 is not equal to 1 squared, which means that x plus 2 is not equal to 1. From this, we get that x is not equal to negative 1. Therefore, the domain of h is the set of all real numbers x greater than or equal to negative 2 and different from negative 1. In other words, all real numbers from negative 2 up to negative 1, including negative 2 and excluding negative 1, and all real numbers strictly greater than negative 1. 4. Substitution. We define the function u such that u of x is the square root of x, and we denote capital X equal to u of x. Therefore, x is equal to capital X squared. Domain of work. The square root of x is defined for x greater than or equal to 0, so capital X is greater than or equal to 0. The initial equation E is equivalent to capital X squared minus 5 times capital X minus 14 equal to 0. Resolution in capital X. We consider the polynomial p of capital X defined by p of capital X equal to capital X squared minus 5 times capital X minus 14. The discriminant delta is equal to the square of negative 5 minus 4 times 1 times negative 14, which is 25 plus 56, equal to 81. That is 9 squared. The two roots are capital X1 equal to negative of negative 5 minus 9 over 2, which is 5 minus 9 over 2, giving negative 2, and capital X2 equal to negative of negative 5 plus 9 over 2, which is 5 plus 9 over 2, giving 7. Return to X. The required condition imposes that capital X must be greater than or equal to 0. The value capital X, 1 equal to negative 2, is rejected because it is strictly less than 0. The value capital X2 equal to 7 is accepted. Therefore, the square root of x equals 7, which means that x equals 7 squared, that is 49. Verification. By substituting back, we obtain 49 minus 5 times the square root of 49 minus 14, which gives 49 minus 35 minus 14, and that equals 0. Set of solutions. The set of solutions is reduced to the single number 49. Before diving into what's next, don't forget to subscribe to stay updated with all the new content. If this helped you, give it a like, share it with someone who might need it, and leave a comment. Your questions and feedback help everyone grow. Dear students, thank you so much for watching this video all the way through. I'll see you again very soon for another session. Until then, take care and goodbye.